This is CS50, and this is week 6, wherein we finally transition from Scratch to C to now Python. And indeed, this is going to be somewhat of a unique experience in that just like a few weeks past, perhaps for the first time, and now today, you're going to learn a new language. But the goal isn't just to throw another fire hose of content and syntax and whatnot at you, but rather to really equip you all to actually teach yourself new languages in the future. And so indeed, what we'll do today, what we'll do this coming week, is sort of prepare you to stand on your own. And once Python is passé and the world has moved on to some other language in some number of years, you'll be well equipped to figure out how to wrap your mind around some new syntax, some new language, and solve problems as well. Now, you'll recall in week 0, this is where we started, just saying hello to the world. And that quickly escalated just a week later in C to be something much, much more cryptic. And if you've still sort of struggled with some of the syntax, find yourself checking your notes or your previous code, like that's totally normal. And that's one of the reasons why there are languages besides C out there, among them this language called Python. Humans over the decades have realized, gee, that wasn't necessarily the best design decision. Or humans have realized, wow, you know what? Now that computers have gotten faster with more memory and faster CPUs, we can actually do more with our programming languages. So just as human languages evolve, so do actual programming languages. And even within a programming language, there's typically different versions. We, for instance, have been using version C11 of C, which was updated in 2011. But Python itself continues to evolve, and it's now up to version 3+. And so there, too, these things will evolve in the coming days. Thankfully, what you're about to see is hello world for the 3rd time, but it's going to be literally this. None of the crazy syntax above or below, fewer semicolons, if any, fewer curly braces, and really a lot of the distractions get out of the way. So to get there, let's consider exactly how we've been programming up until now. So you write a program in C, and you've got hopefully no syntax error, so you're ready to build it, that is compile it. And so you've run make, and then you've run the program like /hello. Or if you think back to week 2, where we took a peek underneath the hood of what make is doing, it's really running the actual compiler, something called Clang, maybe with some command line arguments, creating a program called hello, and then you could do /hello. So today, you're going to start doing something similar in spirit, but fewer steps. No longer will you have to compile your code and then run it, and then maybe fix or change it, and then compile your code and run it, and then repeat. The process of running your code is going to be distilled into just a single step. And the way to think of this for now is that whereas C is frequently used as indeed a compiled language, whereby you convert it first to zeros and ones, Python's going to let you speed things up, whereby you, the human programmer, don't have to compile it. You're just going to run what's called an interpreter, which by design is named the exact same thing as the language itself. And by running this program installed in VS Code or eventually on your own Macs or PCs, this is just going to tell your computer to interpret this code and figure out how to get down to that lower level of zeros and ones. But you don't have to compile the code yourself anymore. So with that said, let's consider what the code is going to look like side by side. In fact, let's look back at some Scratch blocks, just like we did with C in week 1, and do some side by sides. Because even though some of the syntax this week and beyond is going to be different, like the ideas are truly going to be the same. There's not all that much intellectually new just yet. So whereas in week 0, we might have said hello to the world with this purple puzzle piece, today, of course, or rather in week 1, it looked like this in C. But today, moving forward, it's going to quite simply look like this instead. And if we go back and forth for just a moment, here again is the version in C, noticing the very C-like characteristics. And just at a glance here, in Python, I claim it's now this. What do you apparently need not worry about anymore? What's gone? So semicolon is gone, and indeed you don't need those to finish most of your thoughts anymore. Anything else? So the \n is absent, and that's kind of curious because we're still going to get a new line, but we'll see that it's become the default. And this one's a little more subtle, but now the function is called print instead of printf. So it's a little more familiar in that sense. All right, so when it comes to using libraries, that is code that other people have written, in the past we've done things like hash include cs50.h to use cs50's own header file, or standard IO, or standard lib, or string, or any number of other header files you have all used. Well, moving forward, we're going to give you for this first week a similar CS50 library, just very short-term training wheels that will quickly take off, because in reality it's a lot easier to do things in Python, as we'll see. But the syntax for this now is going to be to import the CS50 library in this way. And when we have now this ability, we can actually start writing some code right away. In fact, let me switch over to VS Code here. And just as in the past, I'll create a new file. But instead of creating something called .c, I'm going to go ahead and create my first program called hello.py, using code space hello.py. That, of course, gives me this new tab. And let me actually quite simply do what I proposed, print, quote unquote, hello world, without the \n, without the semicolon, without the f in print. And now let me go down to my terminal window, and I don't have to compile it. I don't have to do /. I instead run a program called Python, whose purpose in life is now to interpret my code top to bottom, left to right. And if I run Python of hello.py, crossing my fingers as always, voila. Now I have printed out hello world. So we seem to have gotten the new line for free in this sense, where it's automatically happening. The $ isn't weirdly on the same line like it once was in week 1, but that's just a minor detail here. If we switch back to now some other capabilities, well, indeed, with the CS50 library, you can also not just import the library itself, but specific functions. And you'll see that temporarily, we're going to give you a helper function called getString, just like in C, that just makes it work exactly the same way as in C. And we'll see a couple of other functions that will just make life easier initially, but quickly will we take those training wheels off so that nothing is indeed CS50 specific. All right, well, how about functions more generally in Python? Let's do a whirlwind tour, if you will, much like we did in that first week of C, comparing one to the other. So back in our world of Scratch, one of the first programs we wrote was this one here, whereby we asked the human their name. We then used the return value that was sort of automatically stored in this answer variable as a second argument to join, so that we could say hello David or hello Carter. So this was back in week 0. In week 1, we converted it to this. And here's a perfect example of things like escalating quickly. And again, this is why we start in Scratch. There's just so much distraction here to achieve the same idea. But even today, we're going to chip away at some of that syntax. So in C, we had to declare the argument as we had to declare the variable as a string here. We, of course, had the semicolon and more. Well, in Python, the comparable code now is going to look more simply like this. So semicolon is again gone on both lines, for that matter. So that's good. What else appears to have changed or disappeared? Yeah? Yeah, so I didn't have to specifically say that answer is now a string. And indeed, Python is dynamically typed. And in fact, it will infer from context exactly what it is you are storing in that variable. Other details that seem a little bit different. A little bit different. What else jumps out at you here? I'll go back. This was the C version. And maybe focus now on the second line, because we've rather exhausted the first. Here's now the Python version. What's different here, yeah? Yeah, there's no %s anymore. There's no second argument at the moment, per se, to print. Now, it is still a little weird. It's as though I've deployed some addition here arithmetically, but that's not the case. Some of you have programmed before, and plus, some of you might know, means what in this context? So to combine, or more technically, anyone know the buzzword? Yeah. To concatenate. So to concatenate is like the fancy way of what Scratch calls joining, which is to take one string on the left, one string on the right, and to join them together, to glue them together, if you will. So this is not addition. It would be if it were numbers involved instead. But because we've got a string, hello, comma, and another string implicitly in this variable based on what the human typed in response to this getString function, that's going to concatenate hello, comma, space, and then David or Carter or whatever the human has typed in. But it turns out there's going to be different ways to do this in Python. And we'll show you a few different ones. And here, too, try not to get too hung up on or frustrated by like all of the different ways you can solve problems. Odds are you're going to be picking up tips and techniques for years to come if you continue programming. So let's just give you a few of the possible ways. So here's a second way. You could print out hello, comma, David or hello, comma, Carter. But what has changed? In the previous version, I used concatenation explicitly. And the space here is important grammatically, just so we get that in the final phrase. Now I'm proposing to get rid of that space, to add a comma outside of the double quotes as well. But if you think back to C, this probably just means that print, similar in spirit to printf, can take not just one argument, but even two. And in fact, because of this comma in the middle that's outside of the double quotes, it's hello, comma, and then it will be automatically concatenated with, even without using the plus, to whatever the value of answer is. And by default, just for grammatical prettiness, the print function always gives you a space for free in between each of the multiple arguments you pass in. We'll see how you can override that down the line. But for now, that's just another way to do it. Now, perhaps the better, if slightly cryptic way to do this, or just the increasingly common way, is probably this third version, which looks a little weird too. And probably the weirdness jumps out. We've suddenly introduced these like curly braces, which I promised were mostly gone, and they are. But inside of this string here, I've done a curly brace, which might mean what, just intuitively? And here is sort of an example of how you learn a new language. Just kind of infer from context how Python probably works. What might this mean? Yeah? Yeah, so this is an indication, because of the curly braces, because this is the way Python was designed, that we want to plug in the value of answer, not literally ANSWER. And the fancy word here is that the answer variable will be interpolated. That is, substituted with its actual value. But, and this is actually weird looking. This was introduced a few years ago to Python. What else did I have to change to make these curly braces work, apparently? Yeah? Yeah, there's this weird f. And so it's sort of like part of printf, but now it's inside the curly, it's inside the parenthesis there. This is just the way Python designed this. So a few years ago, when they introduced what are called format strings, or f strings, you literally prefix your quoted string with the letter f. And then you can use trickery like this, like putting curly braces so that the value will be substituted automatically. If you forget the f, you're going to literally see hello, comma, curly brace, answer, close curly brace. If you add the f, it's indeed interpolated. The value is plugged in. All right, questions on how we can just say hello to the world via Python in this case? Yeah? If you do this without the f, if you omit the f, you will literally see HELLO, comma, curly brace, ANSWER, close curly brace. So in fact, let's do this. Let me go back to VS Code here quickly. I've still got my file called hello.py open. And let me go ahead and change this ever so slightly. So I'm going to go ahead and let's say from CS50 import getString. And that's just the new syntax I propose using to import a function from someone else's library. I'm going to now go ahead and ask the question, let's go ahead and use getString, storing the resultant answer. So getString, quote unquote, what's your name, question mark. And then on this line, I'm going to deliberately make a mistake here, exactly to your question. Let me just say hello, comma, answer. And just this. Now, even though answer is a variable, Python's not going to be so presumptuous as to just plug in the value of a variable called answer. What it's going to do, of course, is if I type in my name, whoops, I typed too fast. Let me go ahead and rerun that again. If I run python of hello.py, type in my name and hit enter, I get hello, comma, answer. Well, let me do one better. Let me apply these curly braces as before. Let me rerun python of hello.py. What's your name? DAVID. And here's again the answer to your question. Now we get literally the curly braces. So the fix here ultimately is just going to be to add the f there, rerun my program again with DAVID, and now hello, comma, David. So this is admittedly a little more cryptic than the ones with the plus or the comma, but this is just increasingly common. Why? Because you can read it left to right. It's nice and convenient. It's less cryptic than the %s. So it's sort of a new and improved version, if you will, of printf in C, based on decades of experience of programmers doing things like this. Questions on printing in this way? We're now on our way to programming in Python. Anything? All right. Well, what more can we do with this language here? Well, let me propose that we consider that we have, for instance, a few other features that we can add to the mix as well. Namely, let's say some data types as well. So let me flip over here to back to the slides. And there's different data types in Python, as we'll soon see. But they're not as explicit as we already saw by using a string from getString. You don't have to explicitly state what it is. But you saw, recall, in C all of these various data types. And then in Python, kind of nicely enough, this list is about to get shorter. And so here is our list in C. Here is an abbreviated list in Python. So we're still going to have strings, but they're going to be more succinctly called strs now, str. We're still going to have ints for integers. We're still going to have floats for floating point values. We're even going to have bools for true and false. But what's missing now from the list is long and floats. And why is that? Or rather, long and double. Well, recall that in C, those used more bits. Well, in Python, the smaller data types previously, int and float, themselves just use more bits for you. And so you don't need to distinguish between small and large. You just use one data type, and the language gives you a bigger range than before. It turns out, though, there's going to be some other features as well of Python, these data types, one of which will be called range, another of which will be list. So gone will be arrays. We'll actually use something literally called a list. Tuples, sort of like XY pairs for coordinates and things like that. Dict for dictionaries. So we'll have built-in capabilities for storing keys and values, we'll see. And even a set. Sort of mathematically, a set is like a collection of values, but it automatically gets rid of duplicates for you. So all of these things we could absolutely implement in C if we wanted. And indeed, in problem set 5, you've been implementing your very own spell checker using some form of hash table. Well, it turns out that in Python, you can solve those same problems, but perhaps a little more readily. In fact, let me go back over here to VS Code. And let me propose that I do the following. Let me go ahead and create a file called dictionary.py. Let me propose that I try to implement, say, problem set 5, our spell checker, in Python instead of C, and achieve ultimately the same kind of behavior whereby I'll be able to spell check a whole bunch of words. So this is jumping the gun a little bit, because you're about to see syntax we'll revisit over the course of today. But for now, I've got a new file called dictionary.py. And let me begin to create some placeholders for functions. We'll see in just a bit that in Python, you can define a function called check. And that check function can take a word as its input. And I'll come back to this in just a moment. In Python, I can define a second function like load, which itself will take a whole dictionary, just like in problem set 5. And I'll go ahead and come back to the implementation of this. Meanwhile, we might similarly implement a function called size, which takes no arguments, but ultimately is going to return the size of my dictionary of words. And then lastly, for consistency with problem set 5, we might define an unload function whose purpose in life is to free any memory that you've been using just to give it back to the computer. Now, odds are, whether you're still working on Speller or have finished Speller, like you wrote a decent amount of lines of code. And indeed, it's been, by design, a challenge. But one of the reasons for these higher level languages like Python is that you can stand on the shoulders of programmers before you and solve very common problems much more quickly, so that you can focus on building your new app or your web application or your own project to solve problems of interest to you. So at the risk of crushing some spirits, let me propose that in Python, if you want a dictionary for something like a spell checker, well, that's fine. Go ahead and give yourself a variable like words to store all of those words, and just assign it equal to a dictionary, or dict for short, in Python. That will give you a hash table. Now, it turns out in Speller, recall, you don't need to worry about words and definitions. It's just about spell checking the words. So strictly speaking, we don't need keys and values. We just need keys. So I'm going to save myself a few more keystrokes by just saying that technically in Python, using a set suffices. Again, a set is just a collection of values with no duplicates. But they don't necessarily have keys and values. It's just one or the other. But now that I have, on line 1, I claim, the equivalent in Python of a hash table, I can actually do something like this. Here's how I might implement the check function in Python. If the word passed into this function is in my variable called words, well, return true. Else, go ahead and return false. Done. Wait, you're thinking, if anything at all, maybe we want to handle lowercase instead of just uppercase and lowercase. Well, you know what? In Python, if you want to force a whole word to lowercase, you don't have to iterate over it with a loop. You don't have to use any of that C-type functions or anything. Just say word.lower, and that will convert the whole thing to lowercase for parity with the dictionary. All right, how about something like the load function in Python? Well, in Python, you can open files just like in C. For instance, in Python, I might do open the dictionary argument in read mode, just like fopen in Python. I might do something like this. For each line in that file, let me go ahead and add to my words variable that line. And then let me go ahead and close that file. And I think I'm done. I'm just going to go ahead and return true just because I think I'm already done. Now here too, I could nitpick a little bit. Technically, if I'm reading in every line from the file, every line in the dictionary ends with technically a \n. But there's an easy way to get rid of that, just like you might in C with an alternative syntax. What I'm actually going to do is this. Let me grab from the current line the current word by stripping off with reverse strip. rstrip, a function we'll again see, that just gets rid of the trailing new line, the \n at the end of that line. And what I really want to do then is add this word to that dictionary. Meanwhile, if I want to figure out what the size is of my dictionary, well, in C, you're probably writing code to iterate over all of those lines, and you're just going to count them up using a variable. Not so in Python. You can just return the length of those words. And better still, in Python, you don't have to manage your own memory. No more malloc, no more free, no more manual thinking about memory. The language just deals with all of that for you. So you know what? It suffices for me to just return true and claim that unloading is done for me. And that's it. Again, whether you're in the middle of or already finished, this might perhaps suggest some frustration, but also enlightenment in that this is why higher level languages exist. You can build on top of the same principles, the same ideas with which you've been dealing, struggling even this past week, but you can now express yourself all the more succinctly. Like this one line implements a hash table for you. And all of this now just uses that hash table in a simpler way. Any questions now on this, keeping in mind that the point nonetheless of Speller and PSET 5 is to understand what's really going on underneath the hood, and better still, to notice this. This might seem all rather amazing, but let me go ahead and do this. I've actually got a couple of versions of Speller written here, and I've got a version written in C that I won't show the source code for, but I'm going to go ahead and make that version of Speller in C. And I'm going to go ahead here and, let's say, split my window here for just a moment. And I'm going to go into a Python version of Speller, really that I just wrote. And on the left-hand side here, let me go ahead and run Speller, the version I compiled in C, using a big text like the Sherlock Holmes text, which is a whole lot of words in it. And on the right-hand side, let me run Python of speller.py, which is a separate file I wrote in advance, just like we give you speller.c. And I'll similarly run this on the Sherlock Holmes text. And I'm going to do my best to hit enter on the left and the right of my screen at the same time. But we should see, hopefully, the same list of misspelled words and the timings thereof. So here we go on the right. Here we go on the left. All right. Sort of a race to see which one wins here. C is on the left. Python is on the right. OK. Interesting. Hopefully, Python's close behind. Note that some of this is internet delay, and so it might not necessarily be a crazy number of seconds, but the system is indeed using, if we measure at a low level, how much time the CPU spent executing my code. C took a total of 1.64 seconds. That was pretty fast, even though it took a moment more for all of the bytes to come over the internet. The Python version, though, took what? 2.44 seconds. So what might an inference be? I mean, one, maybe I'm just better at programming in C than I am in Python, which is probably not true. But what else might you infer from this example? Should we maybe give up on Python, stick with C? No? So what might be going on here? Like, why is the Python version that I claim is correct, and I think the numbers all line up, just not the times, where's the trade-off here? Well, here again is sort of this design trade-off. Yeah. Yeah, exactly. In order to save the human programmer time, there's a lot more features built into Python, more functions, more automatic management of memory, and so forth. And you have to pay a price. Like, someone else's code is doing all of that work for you. But if they've written some number of lines of code, those are just more lines of code that need to be executed for you. Whereas here, the computer is, at the risk of oversimplifying, only running my lines of code. So there's just less overhead. And so this is a perpetual trade-off. Typically, when using a more user-friendly, a more modern language, one of the prices you might pay is performance. Now, there's a lot of smart computer scientists in the world, though, trying to push back on those same trade-offs. And so these interpreters, like the command I wrote, Python, technically can, especially if you run a program again and again, they can actually sort of secretly behind the scenes compile your code for you down to zeros and ones. And then the second, the third, the fourth time you run that program, it might very well be faster. So this is a bit of a head fake here in that I'm running them once and only once, but we could get benefit over time if we kept running the Python version again and again and perhaps fine-tune the performance. But in general, there's going to be this trade-off. Now, would you rather spend the 60 seconds I wrote implementing a spell checker, or the 6 hours, 16 hours you might be or have spent implementing the same in C? You know, probably not. For productivity's sake, this is why we have these additional languages. Just for fun, let me flip over to another screen here and open up a version of Python that's actually on in just a second, on my own Mac instead of the cloud, so that I can actually do something with graphics. So here I just have a black and white terminal window on my very own Mac, and I've pre-installed Python just like we've done so for VS Code in the cloud for you. Notice that I've got this photo of perhaps one of your favorite TV shows here with the cast of The Office. Notice all of the faces in this image here. And let me propose that we try to find one face in the crowd, sort of CSI style, whereby we want to find perhaps the Scranton Strangler, so to speak. And so here is an example of this guy's face. Now, how do we go about finding this specific face in the crowd? Well, our human eyes obviously can pluck him out, especially if you're familiar with the show. But let me go ahead and do this instead. Let me go ahead and propose that we run code that I already wrote in advance here. This is a Python program with more lines of code that we won't dwell on for today, but it's meant to motivate what we can do from a Pillow library, implying a Python image library. I want to import some type of information, some feature called image, so that I can manipulate images, not unlike our own problem set 4. And this is kind of powerful. In Python, you can just import face recognition as a library that someone else wrote. From there, I'm going to create a variable called image. I'm going to use this face recognition's library's load image file function. It's a little verbose, but it's similar in spirit to fopen. And I'm going to open office.jpg. I'm going to then declare a second variable called face locations, plural, because what I'm expecting to get back, per the documentation for this library, is a list of all of the faces locations that are detected. All right, then I'm going to iterate over each of those faces using a for loop that we'll see in more detail. I'm going to then infer what the top, right, bottom, and left corners are of that face. And then what I'm going to do here is show that face alone, if I've detected the face in question. So let me go ahead here and run detect.py. And we'll see not just the one face we're looking for, but if I run python of detect.py, it's going to do all of the analysis. I'll see a big opening here now of all of the faces that were detected in this here program. OK, some better than others, I guess, if you zoom in on catching someone, typical Angela. If you now want to find that one face, I think we need to train the software a bit more. So let me actually open up a second program called Recognize that's got more going on. But let me, with a wave of a hand, point out that I'm now loading not only the office.jpg, but also toby.jpg to sort of train the algorithm to find that specific face. And so now, if I run this second version, recognize.py, with Python of recognize.py, hold my breath for just a moment. It's analyzing presumably all of the faces. You see the same original photo, but do you see one such face highlighted here? This version of the code found Toby, highlighted him with this green, and voila, we have face recognition. So for better or for worse, this is what's happening increasingly societally nowadays. And honestly, even though I didn't write the code live, because it's a good dozen or more lines of code, it's not terribly many. And literally all the authorities, all we have to do is import face recognition, and voila, you have access. Like, these technologies are here already. But let's consider for just a moment, how did we find Toby? Like, how might that library, even though we're not going to look at its implementation details, how does it find Toby and distinguish him from all of these other faces in the crowd? What might it be doing intuitively? Think back even to pset 4, like what you yourselves have access to data-wise. Yeah?
Since you gave it an image of Toby's face from before, it probably looks at, like, are the pixels in one area same as in another area? And a lot of them are the same from that reference image to this new image. And it's going to say, hey, a lot of the similar pixel arrangements are here and here. So we can safely guess that this is the same person.
Yeah, exactly. And to summarize for camera here, we have trained the software, if you will, by giving it a photo of Toby's face. So by looking for the same or really similar pixels, especially if it's a slightly different image of Toby, we can perhaps identify him in the crowd. And what really is a human face? Well, at the end of the day, the computer only knows it as a pattern of bits, or really at a higher level, a pattern of pixels. So maybe a human face is perhaps best defined in general as like 2 eyes and a nose and a mouth, that even though all of us look similar structurally, odds are the measurement between the eyes and the nose and the width of the mouth, the skin tone, and all of these other physical characteristics are patterns that software could perhaps detect and then look sort of statistically through the image, looking for the closest possible match to these various measurements, shapes, colors, and sizes, and the like. And indeed, that might be the intuition, but what's powerful here again is just how easy and readily available this technology now is. All right, so with that said, let's propose to consider what more we can do with Python itself, get back to the fundamentals so that you yourselves can start to implement something along those same lines. So besides having access to things like a getString function, the CS50 library provides a few other things as well. Namely, in C, we had these. But in Python, we're going to have fewer. In Python, our library short term is going to give you not only getString, but also getInt and getFloat. Why? It's actually just kind of annoying, as we'll soon see, to get back an integer or a float from a user and just make sure that it's an int and a float and not like a word like cat or dog or some string that's not actually a number. Well, we can import not just the specific function getString, but we can actually import all of these functions one at a time like this, as we'll soon see. Or you can even in Python import specific functions from a file. One of you asked a while back, when you include something like cs50.h or standardio.h, you're actually getting all of the code in that file, which potentially can add bulk to your own program or time. In this case, when you import specific functions from Python, you can be a little more narrowly precise as to what it is you want to have access to. All right, so with that said, let's go ahead and see what conditionals look like in Python. So in the left-hand side, again, here we'll see Scratch. And here, for instance, was just kind of a contrived example asking if x is less than y, then say x is less than y. In C, it looked like this. In Python now, it's going to look like this instead. And here's before in C, and here's after. And just to call out a few of the obvious differences, what has changed in Python for conditionals, it would seem? Sort of, what's the difference? Yeah? Yeah, so there's no more curly braces, and indeed you don't use those. What appears to be taking their place, if you might infer? What seems to have taken their place? What do you think? So the colon at the start of this line here, but also even more important now is this indentation below it. So some of you, and we know this from office hours, have a habit of like indenting everything on the left, right? And it's just kind of this crazy mess to look at. Frustrating for you, surely. But C and Clang is pretty tolerant when it comes to things like white space in a program. Python, They realized years ago that let's help humans help themselves and just require standard indentation. So 4 spaces would be the norm here. But because it's indented below that colon, that indeed indicates that this now is part of that condition. Something else has gone missing versus C in this conditional. What else is a little simplified? Yeah, so no more parentheses. You can still use them, especially when you need to logically to do order of operations like in math. But in this case, if you just want to ask a simple question like if x less than y, you can just do it like that. How about when you have an if else? Well, this is almost the same here with these same changes. In C, this looked like this. And it's starting to get a bit bulky, at least if we use our curly braces in this way. In Python, we can tighten things up further, even though strictly speaking in C, you don't always need the curly braces. But here, gone are the parentheses again. Gone are the curly braces. Indentation is consistent. And we've just added another keyword else with a colon, but no more semicolons as well. How about something larger like this? An if, else, if, else. This one's a little curious, but in C it looked like this. If, else, if, else. In Python, it now looks like this. And there's perhaps one curiosity here that honestly, all these years later, I still can't remember how to spell it half the time. What's weird about this? What do you spot as different? Yeah, over here. Yeah, instead of else if, it's elif. Why? Apparently else space if was just too many keystrokes for humans to type, so they condensed it into this way. Probably means it's a little more distinguishable too for the computer between the if and the else too, but just something to remember now. It's indeed elif and not else if. All right, so what about variables in Python? I've used a couple of them already, but let's distill exactly how you define and declare these things as well. So in Scratch, if we wanted to create a variable called counter and set it equal initially to 0, we would do something like this. Specify that it's an int, use the assignment operator, end the thought with a semicolon. In Python, it's just simpler. You name the variable, use the assignment operator as before, you set it equal to some value, and that's it. You don't mention the type, you don't mention the semicolon or anything more. What if you want to change a variable like the counter by 1, that is increment it by 1? You have a few different ways here in C. We saw syntax like this, where you can say counter equals counter plus 1, which again feels like illogical. How can counter equal counter plus 1? But again, we read this code really right to left, updating its value by 1. In Python, it's almost the same. You just get rid of the semicolon. So that logic is there. But recall in C, we could do something slightly different that we can also do in Python. In Python, you can also more succinctly do this. Plus equals, and then whatever number you want to add, or you can even change it to subtract if you prefer. Sadly, gone is something you've probably typed a whole lot. What was the other way you can add 1? Plus plus is no more, sadly, in Python. Just too many ways to do the same thing, so they got rid of it in favor of just this syntax here. So keep that in mind as well. What about loops? When you want to do something in Python again and again? Well, in Scratch, in week 0, here's how we meowed 3 times specifically. In C, we had a couple of ways of doing this. This was like the more mechanical approach where you create a variable called I, you set it equal to 0. You then do while I is less than 3, the following, and then you yourself increment I again and again. Mechanical in the sense that like you have to implement all of these gears and make them turn yourself, but this was a correct way to do that. In Python, we can still achieve the same idea, but we don't need the int keyword. We don't need any of the semicolons. We don't need the parentheses. We don't need the curly braces. We can't use the plus plus, so maybe that's a minor step backwards if you're a fan. But otherwise, the code, the logic is exactly the same. But there's other ways to achieve this same idea. Recall that in C, we could also do this. You could use a for loop, which it does exactly the same thing. Both are correct. Both are arguably well designed. It's kind of to each their own when it comes to choosing between these. In Python, though, we're going to have to think through how to do this. So you don't do the same for loop as in C. The closest I could come up with is this, where you say for I, or whatever variable you want to do the counting, in, literally, the preposition, and then you use square brackets here. And we've used square brackets before in the context of like arrays and things like that. And the 0, 1, 2 looks like an array in some sense, even though we've also seen arrays with curly braces. But these square brackets for now denote a list. Python does not have arrays. An array is that contiguous chunk of memory back to back to back that you have to resize somehow by moving things around in memory, as per 2 weeks ago. In Python, though, you can just create a list like this using square brackets. And better still, as we'll see, you can add or even remove things from that list down the road. This, though, is not going to be very well designed. This will work. This will iterate in Python 3 times. But what might rub you the wrong way about this design, even if you've never seen Python before? How does this example not end well? Yeah? Yeah, like if you're making a large list, you have to type out each one of these numbers, like comma 3, comma 4, comma 5, comma dot 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 50, comma dot 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 500. Like surely that's not the best solution to have all of these numbers on the screen wrapping endlessly on the screen. So in Python, another way to do this would be to use a function called range, which technically is a data type unto itself. And this returns to you as many values as you ask for it. Range takes some other arguments as well, but the simplest use case here is if you want back the numbers 0, 1, and 2, a total of 3 values, you say, hey, Python, please give me a range of 3 values. And by default, they start at 0 on up. But this is more efficient than it would be to hard code the entire list at once. And the best metaphor I could come up with is something like this. Like here, for instance, is a deck of cards. This is sort of normal human size. And there's presumably 52 cards here. So writing out 0 through 51 on code would be a little ridiculous for the reasons you note. It would just be very unwieldy and ugly and wrapping and all of that. It would be the virtual equivalent of me like handing you all of these cards at once to just deal with. And right, you know, they're not that big, but like it's a lot of cards to hold on to. It requires a lot of memory or physical storage, if you will. What range does metaphorically is if you ask me for 3 cards, I hand you them one at a time like this, so that at any point in time, you only have one number in the computer's memory until you're handed the next. The alternative, the previous version, would be to hand me all 3 cards at once or all 52 cards at once. But in this case, range is just way more efficient. You can do range of 1,000. That's not going to give you a list of 1,000 values all at once. It's going to give you 1,000 values one at a time, reducing memory significantly in the computer itself. All right, so besides this, what about doing something forever in Scratch? Well, we could do this literally with a forever block, which didn't quite exist in C. In C, we had to hack it together by saying while true, because true is by definition, TRUE, always true. So this just deliberately induces an infinite loop for us. In Python, the logic's going to be almost the same. And infinite loops in Python tend to actually be even more common, because you can always break out of them, as you could in C. In Python, it looks like this. And this is slightly more subtle, but gone are the curly braces, gone are the parentheses, but ever so slight difference too. A capital T for true, and it's going to be a capital F for false. Stupid little differences. Eventually, you're going to mistype one or the other. But these are the kinds of things to keep an eye out and to start recognizing in your mind's eye when you read code. Questions now on any of these building blocks? Yeah? In the for loop was it was set to 0 on the first iteration, then 1 on the next, then 2 on the third. And the same thing for range. It just doesn't use up as much memory all at once. Other questions now on any of these building blocks of Python? No? All right, well, let's go ahead and build something a little more than hello. Let me propose that over here we implement maybe the simplest of calculators here. So let me go back to VS Code here, open my terminal window, and open up, say, a file called calculator.py. And in calculator.py, we'll have an opportunity to explore some of these building blocks, but we'll allow things to escalate pretty quickly to more interesting examples so that we can do the same thing ultimately as well. And in fact, let me go ahead and do this moreover. I've brought some code with me in advance. For instance, something called calculator 0.c from the first week of C. And let me go ahead and split my window here, in fact, so that I can now do something like this. Let me move this over here. Calculator.py. So now I have on the left of my screen calculator.c, or calculator0.c, because that's the first version I made, and calculator.py on the right. Let me go ahead and implement really the same idea here. So on the right-hand side, the analog of including cs50.h would be from cs50 import getInt, if I want to indeed use this function. Now I'm going to go ahead and give myself a variable x without defining its type. I'm going to use this getInt function, and I'm going to prompt the user for x, just like in C. I'm then going to go ahead and prompt the user for another int, like y, here, just like in C. And at the very end, I'm going to go ahead and do print x plus y. And that's it. Now, granted, I have some comments in my C version of the code, just to remind you of what each line is doing. But I've still distilled this into like 6 lines, or really 4 if I get rid of the blank line. So it's already perhaps a bit tighter here. But there's also, it's tighter because something really important historically is missing. What did I seem to omit altogether that we haven't really highlighted yet? Yeah? Yeah, the main function is gone. And in fact, maybe you took for granted that it just worked a moment ago when I wrote hello, but I didn't have a main function in hello either. And this too is a feature of Python and a lot of other languages as well. Instead of having to adhere to these long-standing traditions, if you just want to write code and get something done, fine. Just write code and get something done without necessarily all of this same boilerplate. So whatever is in your Python file, left indented, if you will, by default, is just going to be the code that the interpreter runs top to bottom, left to right. Well, let me go ahead now and run code like this. Let me go ahead and open back up my terminal window, run Python of calculator.py, and I'll do x is 1, y is 2. And as you might expect, it gives me 3. Slight aesthetic bug. I put my space in the wrong place here, so that's a newbie mistake. Let me fix that aesthetically. Let me rerun Python of calculator.py, type in 1, type in 2, and voila, there is now my same version again. But let me propose now that we get rid of this training wheel. We don't want to keep taking 1 step forward and then 2 steps back by adding these training wheels. So let me instead do this. In my version of calculator.py, suppose that we take away already the training wheel that is the CS50 library here. And let me instead then use just Python's built-in function called input, which literally does just that. It gets input from the user. And it stores it, as before, in x and y. So this is not CS50 specific. This is real-world Python programming. Well, let me go ahead and run again Python of calculator.py. And of course, if x is 1 and y is 2, x plus y should, of course, still be 3. It's apparently 12, according to Python, until CS50's library gets involved. But does anyone want to infer what just went wrong? Yeah. Exactly. The input function, by design, always returns a string of text. After all, that's what the human typed in. And even though, yes, I typed the number keys on the keyboard, it's still coming back as all text. Now, maybe we should use like a getInt function. Well, that doesn't exist in Python. All you can do is get textual input, a string from the user. But we can convert one to the other. And so a fix for this, so that we don't accidentally concatenate, that is, join x plus y together, would be to do something like this. Let me go back to my Python code here. And whereas in C, we could previously do typecasting. We could convert one type to another. That generally wasn't the case when you were doing something complex like a string to an int. You could do a char to an int and vice versa. But for a string, recall there was a special function in the C-type library called a to I, like ASCII to integer. That's the closest analog here. And in fact, the way to do this in Python would be to use a function called int, which indeed is the name of the data type too, even though I have not yet had to type it. And I can convert the output of the input function automatically from a string immediately to an int. And now, if I go back to my terminal window, rerun Python of calculator.py with 1 and 2 for x and y, now I'm back in business. So that then is, for instance, what the CS50 library does, if temporarily this week, is it just deals with the conversion for you. And in fact, bad things could happen if I type the wrong thing, like dog or cat instead of a number. But we'll cross that bridge in just a moment as well. All right, what if we do something slightly different now with our calculator? Instead of just addition, let me go ahead and do, how about, instead of addition, let's do division instead. So z equals x divided by y, thereby giving me a third variable z. Let me go ahead and run Python of calculator.py again. I'll type in 1. I'll type in 3 this time. And what problem do you think we're about to see? Or is it gone? What happened when I did this in C, albeit with some slightly more cryptic syntax? When I divided one number, like 1 divided by 3. Anyone recall? Yeah. Yeah, so it would round down to the nearest integer, whereby you experience truncation. So if you take an integer like 1, you divide it by another integer like 3, that technically should be 0.33333, infinitely long. But in C, recall, you truncate the value. If you divide an int by an int, you get back an int, which means you get only the integer part, which was the 0. Now, Python actually handles this for us and avoids the truncation, but it leaves us still with one other problem here, which is going to be, for instance, not necessarily visible at a glance. This looks correct. This has solved the problem in C. So truncation does not happen. The integers are automatically converted to a floating point value. But what other problem did we trip over back in week 1. What else got a little dicey when dealing with simple arithmetic? Anyone recall? Well, the syntax in Python's a little different, but let me go ahead and do this. It turns out in Python, if you want to see more significant digits than what I'm seeing here by default, which is a dozen or so, let me go ahead and print out z as follows. Let me first print out a format string, because I want to format z in an interesting way. And notice this would have no effect on the difference. This is just a format string that for no compelling reason at the moment is interpolating z in those curly braces using an f string or format string. If I run this again with 1 and 3, we'll see indeed the exact same thing. But when you use an f string, you indeed have the ability to format that string more precisely. Just like with %f in Python, you could start to fine tune how many significant digits you see. In C, in Python, you can do the same, but the syntax is a little different. If you want the computer to interpolate z and show you 50 significant digits, that is 50 numbers after the decimal point, syntax is similar to C, but it's a little different. You literally put a colon after the variable's name. .50 means show me the decimal point and then 50 digits to the right. And the f just indicates, please treat this as a floating point value. So now if I rerun Python of calculator.py, divide 1 by 3, unfortunately, Python has not solved all of the world's problems for us. This, again, was an example of floating point imprecision. So that problem is still latent. So just because the world has advanced doesn't necessarily mean that all of our problems from C have gone away. There are solutions using third-party libraries for scientific calculations and the like. But out of the box, floating point imprecision is still an issue. Meanwhile, there was one other problem in C that we ran into involving numbers, and that was this: integer overflow. Recall that an integer in C only took up, what, like 32 bits typically, which meant you could count as high as 4 billion, or maybe if you're doing positive and negatives, as high as 2 billion. After which, weird things would happen. The number would go to 0 or negative, or just it would overflow or wrap back around. Well, wonderfully in Python, they did at least address this, whereby you can count as high as you want. And Python will just use more and more and more and more bits and bytes to store really big numbers, so integer overflow is not a thing. With that said, Python is limited to how many digits it will show you on the screen at once as a string. But mathematically, your math will be correct now. So we've taken a couple steps forward, one step sideways. But indeed, we've solved some of our problems here. All right, questions now on any of these examples thus far? Question. All right, well, how about another problem that we encountered in C? Let's revisit it here in Python as well. So let me go ahead and on the left-hand side here, let me open up a file called, say, compare. Let's see. How about a file called compare3.c on the left? And let me go ahead and create a new file on the right called compare.py. Because recall that bad things happened when we needed to compare two values in C. So on the left here is a reminder of what we once did in C, whereby if we want to compare values, we can get an int in C, stored in x, a get int in C, stored in y. We then have our familiar conditional logic here, just printing out if x is less than y or not. Well, we can certainly do the same thing ultimately in Python by using some fairly familiar syntax. And let's just demonstrate this one quickly. Let me go over here too. I'll do from CS50 import get int, even though I could do this instead with the input function itself. X equals get int, and I'll prompt the user for that. Y equals get int, and I'll prompt the user for that. After that, recall that I can say without parentheses, if x is less than y, then print out, without the f, x is less than y. Then I can go ahead and say else if x is greater than y, I can print out quote unquote x is greater than y. If you'd like to interject now. What did I screw up? Anyway, yeah. elif, right? So elif x is greater than y, else, this part's the same, print x is equal to y. So there's not all that much there's no new logic going on here, but at least syntactically it's a little cleaner. Indeed, this program's only 11 lines long, albeit without any comments. Let me go ahead and run Python of compare.py. Let's see, is 1 less than 2? Indeed. Let's run it again. Is 2 less than 1? No, it's greater than. And let's lastly type in 1 and 1 twice. X is equal to y. So we've got a pretty side-by-side one-to-one conversion here. Let's do something a little more interesting than in C. How about I open instead something where we actually compared for a purpose? So if I open up from from earlier in the course, how about agree.c, which prompt the user to agree to something or not. And let me code up a new version here called agree.py. And I'll do this on the right-hand side with agree.py. But on agree.c on the left, notice that this is how we did this sort of yes-no thing in C. We compared C, a character, equal to single quotes y, or equal to single quotes little y. And then the same thing for n. Now in Python, this one's actually going to be a little bit different here. Let me go ahead and in the Python version of this, let me do something like this. We'll use getString. Well, actually, no, we'll just use input in this case. So let's do s equals input. And we'll ask the user the same thing. Do you agree? Question mark. Then let's go ahead and say if s equals, how about y? How do I do this? Well, a few things. Turns out I'm going to do this. S equals little y. Then I'm going to go ahead and print out agreed. And if s equals capital N or s equals lowercase n, I'm going to go ahead and print out not agreed. And I claimed for the moment that this is identical now to the program on the right, the program on the left in C. But what's different? So we're still doing the same kind of logic, these equals for comparing for equality. But notice that nicely enough, Python got rid of the 2 vertical bars, and it's just literally the word or. If you recall seeing ampersand, ampersand to express a logical and in C, you can just write literally the word and. And so here's a hint of why Python tends to be pretty popular. People just like that it's a little closer to English. There's a little less of the cryptic syntax here. Now, this is correct, as this code will now work, but I've also used double quotes instead of single quotes. And I also omitted a few minutes ago from my list of data types in Python the word char. In Python, there are no chars. There are no individual characters. If you want to manipulate an individual character, you use a string, that is to say a str, of size 1. Now, in Python, you can use single quotes or double quotes. I'm deliberately using double quotes everywhere just for consistency with how we treat strings in C. It's pretty common, though, to use single quotes instead, if only because on most keyboards you don't have to hold the shift key anymore. I mean, humans have really started to optimize just how quickly they want to be able to code. So using a single quote tends to be pretty popular in Python and other languages as well. They are fundamentally the same, single or double, unlike in C where they have meaning. So this is correct, I claim. And in fact, let me run this real quick. I'll open up my terminal window here. Let me get rid of the version in C and run Python of agree.py, and I'll type in y. OK, I'll run it again and type in little y, and I'll stipulate it's going to work for no as well. But this isn't necessarily the only way we can do this. There are other ways to implement the same idea. And in fact, I can go about doing this instead. Let me go back up to my code here. And we saw a hint of this earlier. We know that lists exist in Python, and you can create them just by using square brackets. So what if I simplify the code a little bit and just say if s is in the following list of values, capital Y or lowercase y. It's not all that different logically, but it's a little tighter. It's a little more compact. So if s is in capital N or lowercase n, I can express that same idea too. So here again, it's just getting a little more pleasant to write code. There's less like hitting of the keyboard. You can express yourself a little more succinctly. And using the keyword in, Python will figure out how to search the entire list for whatever the value of s is. And if it finds it, it will return true automatically, else it will return false. So if I run agree.py again and type in capital Y or lowercase y, that still now works. Well, I can tighten this up further if I want to add more features. Well, what if I want to support not just y, big Y and little y, but how about yes, or in case the user's yelling, or someone who isn't good with caps lock types in yes. Wait a minute, but it could be weird. Like, do we want to support this? or this. I mean, this just gets really tedious quickly, combinatorically, if you consider all of these possible permutations. What would be smarter than doing something like this if you want to just be able to tolerate yes in any form of capitalization? Like logically, what would be nice?
Maybe whatever the input is, you just transfer it over to all lowercase or all uppercase and then redo it.
Exactly. Super common paradigm. Why don't we just force the user's input to all lowercase or all uppercase? Doesn't matter so long as we're self-consistent, and just compare against all uppercase or all lowercase. And that will get rid of all of the possible permutations otherwise. Now in C, we might have done something like this. We might have simplified this whole list and just said, let's say we'll do, how about lowercase? So y or yes, and we'll just leave it at that. But we need to force now s to lowercase. Well, in C, we would have used the C-type library. We would have done like toLower and called that function, passing it in, although not really, because in C-type, those operate on individual characters or chars, not whole strings. We actually didn't see a function that could convert a whole string in C to lowercase. But in Python, we're going to benefit from some other feature as well. It turns out that Python supports what's called object-oriented programming. And we're only going to scratch the surface of this in CS50. But if you take a higher level course in programming or CS, you'll explore this as a different paradigm. Up until now in C, we've been focusing on what's called really procedural programming. You write procedures. You write functions, top to bottom, left to right. And when you want to change some value, we were in the habit of using a procedure. That is a function. You would pass something, like a variable, into a function, like toUpper or toLower, and it would do its thing and hand you back a value. Well, it turns out that it would be nicer, programming-wise, if some data types just had built-in functionality. Like, why do we have our variables over here and all of our helper functions, like toUpper and toLower over here, such that we constantly have to pass one into the other? It would be nice to sort of bake into our data types some built-in functionality so that you can change variables using their own default built-in functionality. And so object-oriented programming, otherwise known as OOP, is a technique whereby certain types of values, like a string, aka str, not only have properties inside of them, attributes, just like a struct in C, your data can also have functions built into them as well. So whereas in C, which is not object-oriented, you have structs. And structs can only store data, like a name and a number when implementing a person. In Python, you can, for instance, have not just a structure, otherwise known as a class, storing a name and a number. You can have a function like call that person or email that person or actual verbs or actions associated with that piece of data. Now, in the context of strings, it turns out that strings come with a lot of useful functionality. And in fact, at this URL here, which is in docs.python.org, which is the official documentation for Python, you'll see a whole list of methods, that is, functions that come with strings that you can actually use to modify their values. And what I mean by this is the following. If we go through the documentation, poke around, it turns out that strings come with a function called lower. And if you want to use that function, you just have to use slightly different syntax than in C. You do not do toLower, and you do not say, as I just did, lower, because this function is built into S itself. And just like in C, when you want to go inside of a variable, like a structure, and access a piece of data inside of it, like name or number, when you also have functions built into data types, aka methods. A method is just a function that is built into a piece of data. You can do s dot lower, open paren, close paren in this case. And I can do this down here as well. If s dot lower in quote unquote n or no, the whole thing, I can force this whole thing to lowercase. So the only difference here now is in object-oriented programming, instead of constantly passing a value into a function, you just access a function that's inside of the value. It just works because of how the language itself is defined. And the only way you know whether these functions exist is the documentation, a class, a book, a website, or the like. Questions now on this technique? All right, I claim this is correct. Now, even though you've never programmed, most of you, in Python before, not super well designed. There's a subtle inefficiency now on lines 3 and 5 together. What's dumb about how I've used lower, might you think? Yeah. Yeah, if you're going to use the same function twice and ask the same question, expecting the same answer, why are you calling the function itself twice? Maybe we should just store the result in a variable. So we could do this in a couple of different ways. We, for instance, could go up here and create another variable called t and set that equal to s.lower. And then we could just change this to be t here. But honestly, I don't think we technically need another variable altogether here. I could just do something like this. Let's change the value of s to be the lowercase version thereof. And so now I can quite simply refer to s again and again like this, reusing that same value. Now, to be sure, I have now just lost the user's original input. And if I care about that, if they typed in all caps, I have no idea anymore. So maybe I do want to use a separate variable altogether. But a takeaway here, too, is that strings in Python are technically what we'll call immutable. That is, they cannot be changed. This was not true in C. Once we gave you arrays in week 2 or memory in week 4, you could go to town on a string and change any of the characters you want, uppercasing, lowercasing, changing it, shortening it, and so forth. But in this case, this returns a copy of s forced to lowercase. It doesn't change the original string, that is the memory, the bytes in the computer's memory. When you assign it back to s, you're essentially forgetting about the old version of s. But because Python does memory management for you, there's no malloc, there's no free, Python automatically frees up the original bytes, like YES, and hands them back to the operating system for you. All right, questions now on this technique. Questions on this. In general, I'll call out the Python documentation will start to be your friend, because in class we'll only scratch the surface with some of these things. But in docs.python.org, for instance, there's a whole reference of all of the built-in functions that come with the language, as well as, for instance, those with the string. All right, well, let me go ahead and, before we take a break, let's go ahead and create something a little familiar too, based on our weeks here in C. Let me propose that we revisit those examples involving some meows. So for instance, when we had our cat meow back in the first week and then second in C, we did something that was a little stupid at first, whereby we created a file, as I'll do here, this time called meow.py. And if I want a cat to meow 3 times, I could run it once like this, little copy paste, and now Python of meow.py, and I'm done. Now, we've visited this example like 2 times at least now in Scratch and in C. It's correct, I'll stipulate, but what's obviously poorly designed? What's the fault here? Yeah. It should just be a loop, right? Like, why type it 3 times? Literally copying and pasting is almost always a bad thing, except in C when you have the function prototypes that you need to borrow. But in this case, this is just inefficient. So what could we do better here in Python? Well, in Python, we could probably change this in a few different ways. We could borrow some of the syntax we proposed in slide form earlier, like give me a variable called I, set it to 0, no semicolon. While I is less than 3, if I want to do this 3 times, I can go ahead and print out meow, and then I can do I plus equals 1. And I think this would do the trick, Python of meow.py, and we're back in business already. Well, if I wanted to change this to a for loop, well, in Python, it would be a little tighter, but this would not be the best approach. So for I in 0, 1, 2, I could just do print meow like this, and that too would get the job done. But to our discussion earlier, this would get stupid pretty quickly if you had to keep enumerating all of these values. Like, what did we introduce instead? The range function, exactly. So that hands me back way more efficiently just the values I want, indeed 1 at a time. So even this, if I run it a third or fourth time, we've got the same result. But now let's transition to where we went with this back in the day. How can we start to modularize this? Like, just like it would be nice, I claimed, if MIT had given us a meow function, wouldn't it be nice if, like, Python had given us a meow function? Maybe less compelling in Python, but how can I build my own function? Well, I did this briefly with the spell checker earlier, but let me go ahead and propose that we could implement now our own version of this in Python as follows. Let me go ahead and start fresh here and use the keyword def. So this did not exist in C. You had the return value, the function name, the arguments. In Python, you literally say def to define a function. You give it a name like meow. And now I'm going to go ahead and in this function just print out meow. And this lets me change it to anything else I want in the future. But for now, it's an abstraction. And in fact, I can move it out of sight, out of mind. Just going to hit enter a bunch of times to pretend like now it exists, but I don't care how it is implemented. And up here now I can do something like this. For I in range of 3, let me go ahead and not print meow anymore. Let me just call meow, and tightening up my code further. But I think, let's see, Python of meow.py, this is, I think, going to be the first time it does not work correctly. OK, so here we have, sadly, our first Python error. And let's see. The syntax is going to be different from C or Clang's output. Traceback is like the term of art here. This is like a trace back of all of the lines of code that were just executed, or really functions you called. The file name is uninteresting. This is like my code space specifically, but the file name is important here, meow.py. Line 2 is the issue. OK, I didn't get very far before I screwed up. And then there's a name error. And you'll see in Python there's typically these capitalized keywords that hint at what the issue is. It's something related to names of variables. Meow is not defined. All right, you're programming Python for the first time. You've screwed up. You're following some online tutorial. You're seeing this. Reason through it. Like, why might meow not be defined? What can we infer about Python? How to troubleshoot logically. Maybe. Is it because meow is defined after? You know, as smart as Python seems to be vis-a-vis C, they have some similar design characteristics. So let's try that. So let me scroll all the way back down to where I moved this earlier. Let me get rid of it way down there. I'll copy it to my clipboard. And let me just kind of hack something together. Let me just put it up here. And let's see if this works. So now let me clear my terminal, run Python of meow.py. OK. We're back in business. So that was actually really good intuition, good debugging technique to sort of reason through it. Now, this is kind of contradicting what I claimed back in week 1, which was that, you know, the main part of your program ideally should just be at the top of the file. Like, don't make me look for it. It's not a huge deal with like a 4-line program. But if you've got 40 lines, 400 lines, you don't want like the juicy part of your program to be way down here and all of these functions way up here. So it would be nice maybe if we actually have a main function. And so it actually turns out to be a convention in Python to define a main function. It's not a special function that's automatically called like in C. But humans realized, you know what, that was a pretty useful feature. Let me define a function called main. Let me indent these lines underneath it. Let me practice what I'm preaching, which is put the main code at the top of the file. And wonderfully in Python now, you do not need prototypes. There's none of that hackish copying and pasting of the return type, the name, and the arguments to a function like we needed in C. This is now OK instead, except for one minor detail. Let me go ahead and run Python of meow.py. Hopefully now I've solved this problem by having a main function, but now nothing has happened. All right, even if you've never programmed in Python before, what might explain this behavior? And how do I fix? Again, when you're off in the real world learning some new language, all you have is deductive logic to debug. Yeah?
I remember in C, we actually, even though we put functions underneath the main, we still have to call just the name of the function right above main so that main knew what the function was.
Right. So the solution, to be clear, in C was that we had to put the prototype up here. Otherwise, we'd get an error message. In this case, I'm actually not getting an error message. And indeed, I'll claim that you don't need the prototypes in Python. Just not necessary, because that was annoying, if nothing else. But what else might explain? Yeah, and back? Yeah, maybe you have to call main itself. If main is not some special status in Python, maybe just because it exists isn't enough. And indeed, if you want to call main, the new convention is actually going to be, as the very last line of your program typically, to literally call main. It's a little stupid looking, but you know, they made a design decision, and this is how now we work around it. Python of meow.py now. We're back in business. But now logically, why does this work the way it does? Well, in this case, top to bottom, line 1 is telling Python to define a function called main, and then define it as follows, lines 2 and 3. But it's not calling main yet. Line 6 is telling Python how to define a function called meow, but it's not calling these lines yet. Now, on line 10, you're telling Python call main. And at that point, Python has been trained, if you will, to know what main is on line 1, to know what meow is on line 6. And so it's now perfectly OK for main to be above meow, because you never called them yet. You defined, and then you called. And that's the logic behind this. Any questions now on the structure of this technique here? Now, let's do one more then. Recall that the last thing we did in Scratch and in Python, Scratch and in C was to actually parameterize these same functions. So suppose that you don't want main to be responsible for the loop here. You instead want to very simply do something like meow 3 times and be done with it. Well, in Python, it's going to be similar in spirit to C, but again, we don't need to keep mentioning data types. If you want meow to take some argument, like a number, n, you can just specify n as the name of that argument. Or you could call it anything else, of course, that you want. You don't have to specify int or anything else. In your code now, inside of meow, you can do something like for I in, let's say, I definitely now can't do this, because like that would be weird to start the list and end it with n. So if I can come back over here, what's the solution? How can I do something n times? Yeah, using range. So range is nice because I can pass in now this variable n, and now I can meow, whoops, now I can print out, quote unquote, meow. So it's almost the same as in Scratch, almost the same as in C, but it's a little simpler. And if now I run meow.py, I'll have the ability now to do this here as well. All right, questions on any of this? Right now, we're sort of like taking this stroll through week 1. We're going to momentarily escalate things to look not only at some of these basics, but also other features like we saw with face recognition, with the speller or the like. Because of how many of us are here, we have a huge amount of candy out in the lobby. So why don't we go ahead and take a 10-minute break, and when we come back, we'll do even fancier, more powerful things with Python in 10. All right, so we are back. Among our goals now are to introduce a few more building blocks so that we can solve more interesting problems at the end, much like those that we began with. You'll recall from a few weeks ago, we played with this sort of 2-dimensional Super Mario world, and we tried to print a vertical column of like 3 or more bricks. Well, let me propose that we use this as an opportunity to now tinker with some of Python's more useful, more user-friendly functionality as well. So let me code a file called mario.py, and let's just print out like that, the equivalent of that vertical column. So it's of height 3. Each one is a hash. So let's do for I in range of 3 initially, and let's just print out a single hash. And I think now Python of mario.py, voila, we're in business, printing out just that same pyramid there, or just that same column there. What if, though, we want to print a column of like some variable height, where the user tells us how tall they want it to be? Well, let me go up here, for instance, and instead, how about we'll use, let's do this. How about from CS50 import, how about the getInt function as before? So it will deal with making sure the user gives us an integer. And now, in the past, whenever we wanted to get a number from a user, we've actually followed a certain paradigm. In fact, if I open up here, for instance, how about Mario 1.c from a while back, you might recall that we had code like this. And we specifically use the do while loop in C whenever we want to like get something from the user, maybe again and again and again until they cooperate, at which point we finally break out of the loop. So it turns out Python does have while loops, does have for loops, does not have do while loops. And yet pretty much any time you've gotten user input, you've probably used this paradigm. So it turns out that the Python equivalent of this is to do similar in spirit, but using only a while loop. And a common paradigm in Python, as I alluded earlier, is to actually deliberately induce an infinite loop, while true, capital T, and then do what you want to do, like get an int from the user and prompt them for the height, for instance, in question. And then, if you're sure that the user has given you what you want, like n is greater than 0, which is what I want in this case because I want a positive integer, otherwise there's nothing to print, you literally just break out of the loop. And so we could actually use this technique in C. It's just not really done in C. You could absolutely in C have done a while true loop with the parentheses, lowercase true. You could break out of it and so forth. But in Python, this is like the Python way. And this is actually a term of art. This way in Python is Pythonic. Like this is the way everyone does it, quote unquote. Doesn't mean you have to, but that's sort of the way like the cool Python programmers would implement an idea like this, trying to do something again and again and again until the user actually cooperates. But all we've done is take away the do while loop, but still logically we can implement the same idea. Now below this, let me go ahead and just print out for I in range of n this time, because I want it to be variable and not 3. I can go ahead and print out the hash. Let me go ahead and get rid of the C version here. Open my terminal window, and I'll run again Python of mario.py. I'll type in 3, and I get back those 3 hashes. But if I instead type in 4, I now get 4 hashes instead. So the takeaway here is quite simply that this would be the way, for instance, to actually get back a value in Python that is consistent with some parameter, like greater than 0. How about this? Let's actually practice what we preached a moment ago with our meowing examples and kind of factoring all this out. Let me go ahead and define a main function as before. Let me go ahead and assume for the moment that a getHeight function exists, which is not a thing in Python. I'm going to invent it in just a moment. And now I'm going to go ahead and do something like this. For I in the range of that height, well, let's go ahead and print out those hashes. So I'm assuming that getHeight exists. Let me go ahead and implement that abstraction. So define a function now called getHeight. It's not going to take any arguments in this design. While true, I can go ahead and do the same thing as before. Assign a variable n, the return value of getInt, prompting the user for that height. And then if n is greater than 0, I can go ahead and break. But if I break here, I logically, just like in C, end up executing below the loop in question, but there's nothing there. But if I want getHeight to return the height, what should I type here on line 14 logically? What do I want to return, to be clear? Yeah, so I actually want to return n. And here's another curiosity of Python vis-a-vis C. There doesn't seem to be an issue of scope anymore, right? In C, it was super important to not only declare your variables with the data types, you also had to be mindful of like where they exist inside of those curly braces. In Python, it turns out you can be a little looser with things, for better or for worse. And so on line 11, if I create a variable called n, it exists on line 11, 12, and even 13 outside of the while loop. So to be clear, in C with a while loop, we would have ordinarily had not a colon. We would have had the curly brace like here and over here. And a week ago, I would have claimed that in C, n does not exist outside of the while loop by nature of those curly braces. Even though the curly braces are gone, Python actually allows you to use a variable anytime after you have assigned it a value. So slightly more powerful as such. However, I can tighten this up a little bit. Logically, and this is true in C, I don't really need to break out of the loop by using break. Recall that or know that I can actually, once I'm ready to go, I can just return the value I care about even inside of the loop. And that will have the side effect of breaking me out of the loop and also breaking me out of and returning from the entire function. So nothing too new here in terms of C versus Python except for this issue of scope. And I indeed returned n at the bottom there just to make clear that n would still exist. So either of those are correct. Now I just have a Python program that I think is going to allow me to implement this same Mario idea. So let's run Python of Mario.py. And OK, so nothing happened. Python of Mario.py. What did I do wrong? Yeah, I have to call main. So at the bottom of my code, I have to call main here. And this is a stylistic detail that's been subtle. Generally speaking, when you are writing in Python, there's not a CS50 style guide per se. There's actually a Python style guide that most people adhere to. And in this case, double blank lines between functions is the norm. I'm doing that deliberately, although it might otherwise not be obvious. But now that I've called main on line 16, let's run Mario.py once more. Aha. Now we get there. Now we see it. Type in 3, and I'm back in business printing out the values there. Yeah? Sure, why do I need the if condition at all? Why can't I just return n here as by doing return n? Or if I really want to be succinct, I could technically just do this. The only reason I added the if condition is because if the user types in -1, -2, I wanted to prompt them again and again. That's all. But that would be totally acceptable too if you were OK with that result instead. Well, let me do one other thing here to point out why we are using getInt so frequently, this new training wheel, albeit temporarily. So let me go back to the way it was a moment ago. And let me propose now to take away getInt. I claimed earlier that if you're not using getInt, you can just use the input function itself from Python. But that always returns a string or a str. And so recall that you have to pass the output of the input function to an int, either on the same line or, if you prefer, on another line instead. But it turns out what I didn't do was show you what happens if you don't cooperate with the user, with the program. So if I run Python of Mario.py now, works great, even without the getInt function. And I can do it with 4. Still works great. But let me clear my terminal and be difficult now as the user and type in cat for the height instead. Enter. Now we see one of those tracebacks again. This one is different. This isn't a name error, but apparently a value error. And if I kind of ignore the stuff I don't understand, I can see invalid literal for int with base 10 cat. That's a super cryptic way of saying that cat is not a number in decimal notation. And so I would seem to have to somehow handle this case. And if you want to be more curious, you'll see that this is indeed a trace back. And C tends to do this too, or the debugger would do this for you too. You can see all of the functions that have been called to get you to this point. So apparently my problem is initially in line 14. But line 14, if I keep scrolling, is uninteresting. It's main. But line 14 leads me to execute line 2, which is indeed in main. That leads me to execute line 9, which is in get height. And so, OK, here's the issue. So the closest line number to the error message is the one that probably reveals the most. Line 9 is where my issue is. So I can't just blindly ask the user for input and then convert it to an int if they're not going to give me an int. Now, how do we deal with this? Well, back in problem set 2, you might recall validating that the user typed in a number and using a for loop and the like. Well, it turns out there's a better way to do this in Python, and the semantics are kind of there. If you want to try to convert something for a number to a number that might not actually be a number, turns out Python and certain other languages literally have a keyword called try. And if only this existed for the past few weeks, I know. But like, you can try to do the following with your code. What do I want to try to do? Well, I want to try to execute those few lines, except if there's an error. So I can say except if there's a value error, specifically the one I screwed up and created a moment ago. And if there is a value error, I can print out an informative message to the user like not an integer or anything else. And what's happening here now is literally this operative word try. Python is going to try to get input and try to convert it to an int. And it's going to try to check if it's greater than 0 and then try to return it. Why? All of 3 of those lines are indented underneath the try block. Except if something goes wrong, specifically a value error happens, then it prints this. But it doesn't return anything. And because I'm in a loop, that means it's going to do it again and again and again until the human actually cooperates and gives me an actual number. And so this, too, is what the world would call Pythonic. In Python, you don't necessarily rigorously try to validate the user's input, make sure they haven't screwed up. You honestly take a more lackadaisical approach and just try to do something, but catch an error if it happens. So catch is also a term of art, even though it's not a keyword here. Except if something happens, you handle it. So you try and you handle it. So you sort of best effort programming, if you will. But this is baked into the mindset of the Python programming community. So now if I do Python of Mario.py and I cooperate, works great as before. Try and succeed. 3 works, 4 works. If, though, I try and fail by typing in cat, it doesn't crash, per se. It doesn't show me an error. It shows me something more user-friendly, like not an integer. And then I can try again with dog. Not an integer. I can try again with 5. And now it works. So we won't generally have you write much in the way of these try except blocks, only because they get a little sophisticated quickly. But that is to reveal what the getInt function is doing. This is why we give you the training wheels, so that when you want to get an int, you don't have to jump through all these annoying hoops to do so. But that's all the library is really doing for you, is just try and accept. You won't be left with any training wheels ultimately. Questions now on getting input and trying in this way? Anything at all? Yeah? Say that, oh, could you put the condition outside of the try block? Short answer, yes. And in fact, I struggled with this last night when tweaking this example to show the simplest version. I will disclaim that really, I should only be trying, literally, to do the fragile part. And then down here, I should be really doing what you're proposing, which is do the condition out here. The problem is, though, that logically, this gets messy quickly, right? Because except if there's a value error, I want to print out not an integer. I can't compare n against 0 then, because n doesn't exist because there was an error. So it turns out, and I'll show you this. This is now the advanced version of Python. There's actually an else keyword you can use in Python that does not accompany if or elif. It accompanies try and except, which I think is weirdly confusing. A different word would have been better. But if you really prefer I could have done this instead. And this is one of these design things where like reasonable people will disagree. Generally speaking, you should only try to do the one line that might very well fail. But honestly, this looks kind of stupid now. It's just unnecessarily complicated. And so my own preference was actually the original, which was, yeah, I'm trying a few extra lines that really aren't going to fail mathematically, but it's just tighter. It's cleaner this way. And here's, again, the sort of like, arguments you'll start to make yourself as you get more comfortable with programming. You'll have an opinion. You'll disagree with someone. And so long as you can back your argument up, it's pretty reasonable, probably. All right, so how about we now take away some piece of magic that's been here for a while. Let me go ahead and delete all of this here. And let me propose that we revisit not that vertical column and the exceptions that might result from getting input, but these like horizontal question marks that we saw a while ago. So I want all of those question marks on the same line. And yet I worry we're about to see a challenge here because print, up until now, has been putting new lines everywhere automatically, even without those \n's. Well, let me propose that we do this. For I in the range of 4, if I want 4 question marks, let me just print 4 question marks. Unfortunately, I don't think this is correct yet. Let me run Python of Mario.py. And of course, this gives me a column instead of the row of question marks that I want. So how do we do this? Well, it turns out if you read the documentation for the print function, it turns out that print, not surprisingly perhaps, takes a lot of different arguments as well. And in fact, if you go to the documentation for it, you'll see that it takes not just positional arguments, that is from left to right, separated by commas. Turns out Python supports a fancier feature with arguments where you can pass the names of arguments to functions too. So what do I mean by this? If I go back to VS Code here, and I've read the documentation, it turns out that yes, as before, you can pass multiple arguments to Python like this, like hello, comma, David, comma, Malin. That will just automatically concatenate all 3 of those positional arguments together. They're positional in the sense that they literally flow from left to right, separated by commas. But if you don't want to just pass in values like that, you want to actually print out, as I did before, a question mark. But you want to override the default behavior of print by changing the line ending. You can actually do this. You can use the name of an argument that you know exists from the documentation and set it equal to some alternative value. And in fact, even though this looks cryptic, this is how I would override the end of each line to be quote unquote, that is nothing. Because if you read the documentation, the default value for this end argument, does someone want to guess, is \n. So if you read the documentation, you'll see that \n is the implied default for this end argument. And so if you want to change it, you just say end equals something else. And so here, I can change it to nothing and now rerun Python of Mario.py. And now they're all on the same line. Now, it looks a little stupid because I made that sort of week 1 mistake where I still need to move the cursor to the next line. That's just a different problem. I'm just going to go over here and print nothing. I don't even need to print \n, because if print automatically gives you a \n, just call print with nothing, and you'll get that for free. So let me rerun Python of Mario.py, and now it looks a little prettier at the prompt. And to be super clear as to what's going on, suppose I want to sort of make an exclamation here. I could change the \n default to like an exclamation point just for kicks. And if I run Python of Mario.py again, now I get this sort of exclamation with question marks and exclamation points as well. So that's all that's going on here. And this is what's called a named argument. It literally has a name that you can specify when calling it in. And it's different from positional in that you're literally using the name. Let me propose something else, though. And this is why people kind of like Python. There's just kind of cool ways to do things. That's kind of a, it's a 3-line verbose way of printing out 4 question marks. I could certainly take the, shortcut and just do this, but that's not really that interesting for anyone, especially if I want to do it a variable number of times. But Python does let you do this. If you want to multiply a character some number of times, not only can you use plus for concatenation, you can use star or an asterisk for multiplication, if you will. That is concatenation again and again and again. So if I just print out quote unquote question mark times 4, that's actually going to be the tightest way, the most succinct way I can print 4 question marks instead. And if I don't use 4, I use n, where I get n from the user. Bang, like now I've gotten rid of the for loop entirely, and I'm using the star operator to manipulate it instead. And to be super clear here, insofar as Python does not have malloc or free or memory management that you have to do. Guess what Python also doesn't have? Anything on your minds in the past couple of weeks? Doesn't have pointers. Yeah, so Python does not have pointers, which just means that all of that happens for you automatically underneath the hood, again, by way of code that someone else wrote. How about one more throwback with Mario? We talked about in week 1 this sort of 2-dimensional structure where it's like, I claim, like 3 by 3, a grid of bricks, if you will. Well, how can we do this in Python? We can do this in a couple of ways now. Let me go back to my mario.py, and let me do something like for I in range of, we'll just do 3, even though I know now I could use getInt, or I could use input and int. And if I want to do something 2-dimensionally, just like in C, you can nest your for loops. So maybe I could do for j in range of 3. And then in here, I could print out a hash symbol. And then let's see if that gives me 9 total. So if I've got a nested loop like this, Python of mario.py hopefully gives me a grid. No, it gave me a column of 9. Why, logically? Even though I've got my row and my columns. Yeah. Yeah, the line ending. So in my row, I can't let print just keep adding new line. So I just have to override this here. And let me not screw up like before. Let me print one at the end of the whole row just to move the cursor down. And I think now together, now we've got our 3 by 3. Of course, we could tighten this up further. Like if I don't like the nested loop, I probably could go in here and just print out, for instance, a brick times 3, or I could change the 3 to a variable if I've gotten it from the user. So I can tighten this up further. So again, just different ways to solve the same problem. And again, sort of evidence of why a lot of people like Python. There's just some more pleasant ways to solve problems without getting into the weeds constantly of doing things like with for loops and while loops endlessly. All right, well, how about some other building blocks? Lists are going to be so incredibly useful in Python, just as arrays were in C. But arrays are annoying because you have to manage the memory yourself. You have to know in advance how big they are, or you have to use pointers and malloc or realloc to resize them. Like, oh my god, like the past 2 weeks have been painful in that sense. But Python does this all for free for you. In fact, there's a whole bunch of functions that come with Python that involve lists, and they'll allow us ultimately to do things again and again and again within the same data structure. And for instance, we'll be able to get the length of a list. You don't have to remember it yourself in a variable. You can just ask Python how many elements are in this list. And with this, I think we can solve some old problems too. So let me go back here to VS Code. Let me close Mario and give us a new program called scores.py. And rather than show the C and the Python now, let's just focus on Python. And in scores.c, way back when, we just averaged like 3 test scores or something like that, 72, 73, and 33 a few weeks ago. So if I want to create a list in this Python version of 72, 73, 33, I just use my square bracket notation. C let you use curly braces if you know the values in advance, but Python's just this. And now if I want to compute the average, in C, recall, I did something with a loop. I added all the values together. I then divided by the total number of values, just like you would in grade school, and that gave me the average. Well, Python comes with a lot of super handy functions, not just length, but others as well. And so in fact, if you want to compute the average, you can take the sum of all of those scores and divide it by the length of all of those scores. So Python comes with length, comes with sum. You can just pass in a whole list of any size and let it deal with that problem for you. So if I want to now print out this average, I can print out average colon, and then I'll plug in my average string for a variable for interpolation. Let me make this an f string so that it gets formatted. And let me just run Python of scores.py. And there's my average. It's sort of rounding weird because we're still vulnerable to some floating point imprecision. But at least I didn't need loops, and I didn't have to write all this darn code just to do something that, you know, Excel and Google Spreadsheets can just do like that. Well, Python is closer to those kinds of tools, but more powerful in that you can manipulate the data yourself. How about, though, if I want to get a bunch of scores manually from the user and then sum them together? Well, let's combine a few ideas here. How about this? First, let me go ahead and import the CS50 getInt function from the CS50 library, just so we don't have to deal with try and accept or all of that. And let me go ahead and give myself an empty list. And this is powerful. In C, there's no point to an empty array, because if you create an empty array with square bracket notation, like, it's not useful for anything. But in Python, you can create it empty because Python will grow and shrink the list for you automatically as you add things to it. So if I want to get 3 scores from the user, I could do something like this. For I in range of 3. And then I can grab a variable called score or anything. I could call getInt, prompt the human for the score that they want to type in. And then once they do, I can do this, thinking back to our object-oriented programming capability now. I could do scores dot append, and I can append that score to it. And you would only know this from having read the documentation, heard it in class in a book or whatnot. But it turns out that just like strings have functions like lower built into them, lists have functions like append built into them that just literally appends to the end of the list for you, and Python will grow or shrink it as needed. No more malloc or realloc or the like. So this just appends to the scores array, the scores list, that score, and then again and again and again. So the array starts at, the list starts at size 0, then grows to 1, then 2, then 3, without you having to do anything else. And so now down here, I can compute an average with the sum of those scores divided by the length of the total number of scores. And to be clear, length is the total number of elements in the list. Doesn't matter how big the values themselves are. Now I can go ahead and print out an f string with something like average, colon average in curly braces. And if I run python of scores.py, I'll type in, just for the sake of discussion, the 3 values. I still get the same answer. But that would have been painful to do in C unless you committed in advance to a fixed size array, which we already decided weeks ago was annoying, or you grew it dynamically using malloc or realloc or the like. All right, what else can I do? Well, there's some nice things you might as well know exist. Instead of scores.append, you can do slight fanciness like this. Like if you want to append something to a list, you can actually do plus equals and then put that thing in a temporary list of its own and just use what is essentially concatenation, but not concatenation of strings, but concatenation of lists. So this new line 6 appends to the scores list this tiny little list I'm temporarily creating with just the current new score. So just another piece of syntax that's worth seeing that allows you to do something like that as well. All right, well, how about we go back to strings for a moment? And all of these examples, as always, are on the course's website afterward. Suppose we want to do something like converting characters to uppercase. Well, to be clear, I could do something like this. Let me create a program called uppercase.py. Let me prompt the user for a before string, as by using the input function or getString, which is almost the same. And I'll prompt the user for a string beforehand. Then let me go ahead and print out, how about the keyword after, and then end the new line with nothing, just so that I can see before on one line and after on the next line. And then let me do this. And here's where Python gets pleasant too with loops. For C in before, print c.upper end equals quote unquote, and then I'll print this here. All right, that was fast, but let's try to infer what's going on. So line 1 just gets input from the user, stores it in a variable called before. Line 2 literally just prints after, but doesn't move the new line, the cursor to the next line. What it then does is this. And in C, this was a little more annoying. You needed a for loop with I. You needed array notation with the square brackets. But Python, if you say for variable in string, so for C, for character in string, Python's going to automatically assign C to the first letter that the user types in. Then on the next iteration, the second letter, the third letter, and the fourth. So you don't need any square bracket notation. You just use C, and Python will do it for you and just hand you back one at a time each of the letters that the user has typed in. So if I go back over here and I run, for instance, python of uppercase.py, and I'll type in, how about David in all lowercase and hit enter, you'll now see that it's all uppercase instead by iterating over it, indeed one character at a time. But we already know, thanks to object-oriented programming, strings themselves have the functionality built in to not just uppercase single characters, but the whole string. So honestly, this was a bit of a silly exercise. I don't need to use a loop anymore like in C. And so some of the habits you've only just developed in recent weeks, it's time to start breaking them when they're not necessary. I can create a variable called after, set it equal to before.upper, which indeed exists, just like .lower exists. And then what I can go ahead and print out is, for instance, let's get rid of this print line here and do it at the end, after, and print the value of that variable. So now if I rerun uppercase.py, type in David in all lowercase, I can just uppercase the whole thing all at once, because again, in Python, you don't have to operate on characters individually. Questions on any of these tricks up until now? No? All right, how about a few other techniques that we saw in C that we'll bring back now in Python? So it turns out in Python, there are other libraries you can use too that unlock even more functionality. So in C, if you wanted command line arguments, you just change the signature for main to be void, instead of void, to be int argc, comma, string argv, open brackets for an array, or char star eventually. Well, it turns out in Python that if you want to access command line arguments, it's a little simpler, but they're tucked away in a library, otherwise known as a module called sys, the sys or system module. Now, this is similar in spirit to the CS50 library in that it's got a bunch of functionality built in, but this one comes with Python itself. So if I want to create a program like greet.py in VS Code here, let me go ahead and do this. From the sys library, let's import argv. And that's just a thing that exists. It's not built into main because there is no main per se anymore. So it's tucked away in that library. And now I can do something like this. If the length of argv equals 2, well, let's go ahead and print out something friendly like hello, comma, argv bracket 1, and then close quotes. Else, if the length of argv is not equal to 2, let's just go ahead and print out hello world. Now, at a glance, this might look a little cryptic, but it's identical to what we did a few weeks ago. When I run this Python of greet.py with no arguments, it just says hello world. But if I instead add a command line argument, like my first name, and hit enter, now the length of argv is no longer 1, it's going to be 2. And so it prints out hello David instead. So the takeaway here is that whereas in C, argv technically contained the name of your program, like /hello or /greet, and then everything the human typed. Python's a little different in that because we're using the interpreter in this way, technically when you run Python of greet.py, the length of argv is only 1. It contains only greet.py. So the name of the file, it does not unnecessarily contain Python itself, because what's the point of that being there omnipresently? It does contain the number of words that the human typed after Python itself. So argv is length 1 here, argv is length 2 here, and that's why when it did equal 2, I saw hello David instead of the default hello world. So same ability to access command line arguments, add these kinds of inputs to your functions, but you have to unlock it by way of using argv instead in this way. If you want to see all of the words, you could do something like this. Just as if we combine ideas here, for I in range of, how about length of argv, then I can do this, print argv bracket I. All right, a little cryptic, but line 3 is just a for loop, iterating over the range of length of argv. So if the human types in 2 words, the length of argv will be 2. So this is just a way of saying iterate over all of the words in argv, printing them one at a time. So Python of greet.py, enter, just prints out the name of the program. Python of greet.py with David prints out greet.py and then David. I can keep running it, though, with more words, and they'll each get printed one at a time. But what's nice, too, about Python, and this is the point of this exercise, honestly, this looks pretty cryptic. This is not very pleasant to look at. If you just want to iterate over every word in a list, which argv is, watch what I can do. I can do for arg, or any variable name, in argv. Let me just now print out that argument. I could keep calling it I, but I seems weird when it's not a number, so I'm changing to arg as a word instead. If I now do Python of greet.py, it does this. If I do Python of greet.py David, it does that again. David Malin, it does that again. So this is, again, why Python is just very appealing. You want to do something this many times, iterate over a list, just say it. And it reads a little more like English. And there's even other fanciness, too, if I may. It's a little stupid that I keep seeing the name of the program, greet.py. So it'd be nice if I could remove that. Python also supports what are called slices of arrays. Slices of lists. Even I get the terminology confused. If argv is a list, then it's going to print out everything in it. But if I want a slice of it that starts at location 1 all the way to the end, you can use this funky syntax in between the square brackets, which we've not seen yet, that's going to start at item 1 and go all the way to the end. And so this is a nice, clever way of slicing off, if you will, the very first element, because now when I run greet.py David Malan, I should only see David and Malan. If I only want one element, I could do 1 to 2. If I want all of them, I could do 0 onward. I could give myself just one of them in this way, so you can play with the start value and the end value in this way to sort of slice and dice these lists in different ways. That would have been a pain in C just because we didn't really have the built-in support for manipulating arrays as cleanly as this. All right, just so you've seen it too, though this one is less exciting to see live, if I go ahead and create a quick program here, it turns out there's something else in the sys library, the ability to exit programs, either exiting with status code 1 or 0, as we've been doing anytime something goes right or wrong. So for instance, let me whip up a quick program that just says if the length of sys.argv does not equal 2, then let's yell at the user and say, you're missing a command line argument. Otherwise, command line argument. And let's then return sys.exit1. Else, let's go ahead and logically just say print a formatted string that says hello as before, sys.argv1. Now, things look different all of a sudden, but I'm doing something deliberately. First, let's see what this does. So on line 1, I'm importing not argv specifically. I'm importing the whole sys library, and we'll see why in a second. Well, it turns out that the sys library has not only the argv list, it also has a function called exit, which I'd like to be able to use as well. So it turns out that if you import a whole library in this way, that's fine, but you have to refer to the things inside of it by using that same library's name and a dot to sort of namespace it, so to speak. So here I'm just saying if the user does not type in 2 words, yell at them with missing command line argument and then exit with 1. Just like in C, when you do exit 1, just means something went wrong. Otherwise, print out hello to this. And this is starting to look cryptic, but it's just a combination of ideas. The curly braces mean interpolate this value, plug it in here. Sys.argv is just the verbose way of saying go into the sys library and get the argv variable therein. And bracket 1, of course, just like arrays in C, is just the second element at the prompt. So when I run this version now, Python of exit.py, with no arguments, I get yelled at in this way. If, however, I type in 2 arguments total, the name of the file and my own name, now I get greeted with hello, David. And it's the same idea before. This was a very low-level technique, but same thing here. If you do echo $? Enter, you'll see the exit code of your program. So if I do this incorrectly again, let me rerun it without my name, enter, I get yelled at. But if I do echo $? There's the secret 1 that's returned. Again, just to show you parity with C in this case. Questions now on any of these techniques here? All right, how about something that's a little more powerful too? We spent so much time in week 0 and 1 doing searching and then eventually sorting in week 3. Well, it turns out Python can help with some of this too. Let me go ahead and create a program called names.py that's just going to be an opportunity to maybe search over a whole bunch of names. Let me go ahead and import sys. And then just so I have access to exit. And let me go ahead and create a variable called names that's going to be a list with a whole bunch of names. How about here? Charlie and Fred and George and Ginny and Percy and lastly Ron. So a whole bunch of names here. And it'd be a little annoying to implement code that iterates over that from left to right in C, searching for one of those names. In fact, what name? Well, let's go ahead and ask the user to input the name that they want to search for so that we can tell them if the name is there or not. And we could do this similar to C in Python, doing something like this. So for n in names, where n is just a variable to iterate over each name, if how about the name I'm looking for equals the current name in the list, aka n, well, let's print out something friendly like found. And then let's do sys.exit0 to indicate that we found whoever that is. Otherwise, if we get all the way to the bottom here outside of this loop, let's just print not found, because if we haven't exited yet, and then let's just exit with 1. Just to be clear, I can continue importing all of sys, or I could do from sys import exit, and then I could get rid of sys dot everywhere else. But sometimes it's helpful to know exactly where functions came from. So this too is just a matter of style in this case. All right, so let's go ahead and run this. Python of names.py, and let's look for like Ron all the way at the end. All right, he's found. And let's search for someone outside of the family here, like Hermione. Not found. OK, so it seems to be working in this way. But I've essentially implemented what algorithm? What algorithm would this seem to be per lines 7 and 8 and 9 and 10? Yeah, so it's just linear search. It's a loop, even though the syntax is a little more succinct today. And it's just iterating over the whole thing. Well, honestly, we've seen an even more terse way to do this in Python. And this, again, is what makes it a more pleasant language sometimes. Why don't I just do this? Instead of iterating one at a time, why don't I just say this? Let me go ahead and change my condition to just be, how about if the name we're looking for is in the names list, we're done. We found it. Use the in preposition that we've seen a couple of times now that itself asks the question, is something in something else? And Python will take care of linear search for us. And it's going to work exactly the same. If I do Python of names.py, search for Ron, it's still going to find him. And it's still going to do it linearly in this case, but I don't have to write all of the lower level code myself in this case. Questions now on any of this? The code's just getting shorter and shorter. Now, what about, let's see, what else might we have here? How about this? It turns out, let's go ahead and implement that phone book that we started metaphorically with in the beginning of the course. Let's code up a program called phonebook.py. And in this case, let's go ahead and let's create a dictionary this time. Recall that a dictionary is a little something that implements something like this, like a 2-column table that's got keys and values, words and definitions, names and numbers. And let's focus on the last of those, names and numbers in this case. Well, I claimed earlier that Python has built-in support for dictionaries, dict objects that you can create with one line. I didn't need it for Speller because a set is sufficient when you only want one of the keys or the values, not both. But now I want some names and numbers. So it turns out in Python, you can create an empty dictionary by saying dict open parenthesis close, and that just gives you essentially a chart that looks like this with nothing in it. Or there's more succinct syntax. You can alternatively do this with 2 curly braces instead. And in fact, I've been using a shortcut all this time. When I had a list earlier where my variable was called scores, and I did this, that was actually the shorthand version of this. Hey, Python, give me an empty list. So there's different syntax for achieving the same goal. In this case, if I want a dictionary for people, I can either do this or, more commonly, just 2 curly braces like that. All right, well, what do I want to put in this? Well, let me actually put some things in this. And I'm going to just move my close curly brace to a new line. If I want to implement this idea of keys and values, the way you do this in Python is key, value. Comma, key, value. So you'd implement it more in code. So for instance, if I want Carter to be the first key in my phone book, and I want his number to be +1 617 495 1000, I can put that as the corresponding value. The colon is in between. Both are strings or strs, so I've quoted both deliberately. If I want to add myself, I can put a comma. And then just to keep things pretty, I'm moving the cursor to the next line. But that's not strictly required aesthetically. It's just good style. And here I might do +1 949 468 2750. And now I have a dictionary that essentially has 2 rows here, Carter and his number, and David and his number as well. And if I kept adding to this chart would just get longer and longer. Suppose I want to search for one of our numbers. Well, let's prompt the user for the name for whose number you want to search by getting string. Or you know what? We don't need the CS50 library. Let's just use input and prompt the user for a name. And now we can use this super terse syntax and just say if name in people print the formatted string number, and here we can do this, people bracket name. OK, so this is getting kind of cool, kind of quickly, kind of confusingly. So let me run this. Python of phonebook.py. Let's type in Carter, and indeed I see his number. Let's run it again with David, and I see my number here. So what's going on? Well, it turns out that a dictionary is very similar in spirit to a list. It's actually very similar in spirit to an array in C, but instead of being limited to keys that are numbers, like bracket 0, bracket 1, bracket 2, you can actually use words. And that's all I'm doing here on line 8. If I want to check for the name Carter, which is currently in this variable called name, I can index into my people dictionary using not a number, but using literally a string, the name Carter or David or anything else. To make this clearer too, notice that I'm at the moment using this format string, which is adding some undue complexity. But I could clarify this perhaps further as this. I could give myself another variable called number, set it equal to the people dictionary, indexing into it using the current name. And now I can shorten this to make it clearer that all I'm doing is printing the value of that. And in fact, I can do this even more cryptically this would be weird to do, but if I only ever want to show David's phone number and never Carter's, I can literally, quote unquote, index into the people dictionary, because now when I run this, even if I type Carter, I'm going to get back my number instead. But that's all that's happening if I undo that, because that's now a bug. But I index into it using the value of name. Dictionaries are just so wonderfully convenient because now you can associate anything with anything else, but not using numbers, but entire keywords instead. So here's how if in Speller we gave you not just words, but hundreds of thousands of definitions as well, you could essentially store them as this. And then when the human wants to look up a definition in a proper dictionary, not just for spell checking, you could index into the dictionary using square brackets and get back the definition in English as well. Questions on this? Yeah?
Is the way that this code does it, because I know you're saying that Python has functions already made for you, is the in preposition actually iterate through an array to find the value? Or because you're calling the value here, it must still find a way to go to location and find it?
A really good question. So to summarize, how is Python finding that name within that dictionary? This is where, honestly, Speller in PSET 5 is what Python's all about. So you are struggling with implementing your own spell checker and implementing your own hash table. And recall that per last week, the goal of a hash table is to ideally get constant time access, not something linear, which is slow, and even better than something logarithmic like log base 2 of n. So Python and the really smart people who invented it, they have written the code that does its best to give you constant time searches of dictionaries. And they're not always going to succeed, just as you in your own problem set probably going to have some collisions once in a while and start to have chains of linked lists of words. But this is where, again, you defer to someone else, someone smarter than you, someone with more time than you to solve these problems for you. And if you read Python's documentation, you'll see that it doesn't guarantee constant time, but it's going to ideally optimize the data structure for you to get as fast as possible. And of all of the data structures, like a dictionary, a hash table is really like the Swiss Army knife of computing, because it just lets you associate something with something else. And even though we keep focusing on names and numbers, that's a really powerful thing, because it's more powerful than lists and arrays, which are only numbers and something else. Now you can have any sorts of relationships instead. All right, let me show a few other examples before we culminate with some more powerful techniques in Python's thanks to libraries. How about this problem we encountered in week 4, which was this? Let me code up a program called, again, compare.py here. But this time, compare two strings and not numbers. So let me, for instance, get one string from the user called s. Just for the sake of discussion, let me get another string from the user called t, so that we can actually do some comparison here. And if s equals t, let's go ahead and print out that they're the same. Else, let's go ahead and print out that they're different. So this is very similar to what we did in week 4. But in week 4, recall, we did this specifically because we had encountered a problem. For instance, if I run, what's going on? Input T. Come on. Oh, duh. OK. Wow. OK. Long day. All right. If I run the proper command, Python of compare.py, then let's go ahead and type in something like cat in all lowercase, cat in all lowercase, and they're the same. If, though, I do this again with dog and dog, they're the same. And of course, cat and dog, they're different. But does anyone recall from 2 weeks ago when I typed in my name twice, both identically capitalized, what did it say? That they were, in fact, different. And why was that? Like, why were two strings in C different, even though I typed literally the same thing? Two different places in memory. So each string might look the same aesthetically, but of course was stored elsewhere in memory. And yet Python appears to be using the equality operator, equals equals, like you and I would expect as humans, actually comparing for us char by char in each of those strings for actual equality. So this is a feature of Python in that it's just easier to do. And why? Well, this derives from the reality that in Python there are no pointers anymore. There's no underlying memory management. It's not up to you now to worry about those lower level details. The language itself takes care of that for you. And so similarly, if I do this and don't ask the user for two strings, but just one, and then I do something like this, how about give myself a second variable t, set it equal to s.capitalize, which note is not the same as upper. Capitalize by design per Python's documentation will only capitalize the first letter for you. I can now print out, say, two f strings here, what the value of s is. And then let me print out with another f string what the value of t is. And recall that in C, this was a problem because if you capitalize s and store it in t, we accidentally capitalized both s and t. But in this case, in Python, when I actually run this and type in cat in all lowercase, the original s is unchanged, because when I use capitalize on line 3, this is indeed capitalizing s, but it's returning a copy of the result. It cannot change s itself because, again, for that technical term, s is immutable. Strings, once they exist, cannot be changed themselves, but you can return copies and modified, mutated copies of those same strings. So in short, all of those headaches we encountered in week 4 are now solved really in the way you might expect. And here's another one that we dwelled on in week 4 with the colored liquid in glasses. Let me code up a program called swap.py. And in swap.py, let me set x equal to 1, y equal to 2. And then let me just print out an f string here. So how about x is this, comma, y is that. And then let me do that twice, just for the sake of demonstration. And in here, recall that we had to create a swap function, but then we had to pass it in by reference with the ampersand. And like, oh my god, like that was kind of peak complexity in C. Well, if you want to swap x and y in Python, you could do x comma y equals y comma x. And now Python of swap.py, and there we go. All of that's handled for you. It's sort of like a shell game without even a temporary variable in mind. So what more can we do here? How about a few final building blocks? And these related now to files from that week 4. Suppose that I want to save some names and numbers in like a CSV file, comma separated values, which is like a very lightweight spreadsheet. Well, first, let me create a phonebook.csv file that just has name, comma, number as like the first row there. But after that, I'm going to go ahead now and code up a phonebook.py program that actually allows me to add things to this phone book. So let me split my screen here so that we can see the old and the new. And down here in my code for phonebook.py, in this new and improved version, I'm going to actually import a whole other library, this one called CSV. And here too, especially for people in data science and the like, really like being able to manipulate files and data that might very well be stored in spreadsheets or CSVs, comma, separated values, which we saw briefly in week 4. In phonebook.py then, it suffices to just import CSV after reading the documentation therefore, because this is going to give me functionality in code related to CSV files. So here's how I might open a file in Python. I literally call open. It's not fopen now. It's just open. And I open this file called phonebook.csv. And just as in C, I'm going to open it in append mode. Not write, where it would change the whole thing. I want to append, new line at a time. After this, I want to get maybe, how about a name from the user? So let's prompt the user for some input for their name. And then let's prompt the user for a number as well using input, prompting for number. All right, and now this is a little cryptic, and you'd only know this from the documentation. But if you want to write rows to a CSV file that you can then view in Excel or the like, you can do this. Give me a variable called writer, but I could call it anything I want. Let me use a csv.writer function that comes with this CSV library, passing in the file. This is like saying, hey, Python, treat this open file as a CSV file so that things are separated with commas and nicely formatted in rows and columns. Now I'm going to do this. Use that writer to write a row. Well, what do I want to write? I want to write a short list, namely the current name and the current number to that file. But I don't want to use fprintf and %s and all of that stuff that we might have had in the past. And now I just want to close the file. Let me reopen my terminal. Let me run Python of phonebook.py. And let me type in, how about David, and then +1 949 468 2750, and crossing my fingers, watching the actual CSV at top left, my code has just added me to the file. And if I were to run it again, for instance, with Carter and +1 617 495 1000, crossing my fingers again, we've updated the file. And it turns out there's code now via which I can even read that file, but I can first tighten this up just so you've seen it. It turns out in Python, it's so common to open files and close them. You know, humans make mistakes, and they often forget to close files, which might then end up using more memory than you intend. So you can alternatively do this in Python so that you don't have to worry about closing files. You can use this keyword instead. You can say, with the opening of this file as a variable called file, do all of the following underneath. So I'm indenting most of my code. I'm using this new Python-specific keyword called with. And this is just a matter of saying, with the following opening of the file, do those next 4 lines of code, and then automatically close it for me at the end of the indentation. It's a minor optimization, but this, again, is sort of the Pythonic way to do things instead. How else might I do this too? Well, it turns out that the code I've written here, on line 9 especially, is a little fragile, right? If any human opens this spreadsheet, the CSV file in Excel, Google Spreadsheets, Apple Numbers, and maybe like moves the columns around just because maybe they're futzing, they save it, and they don't realize they've now changed my assumptions, I don't want to necessarily write name and number always in that order, because what if someone screws up and flips those 2 columns by literally dragging and dropping? So it turns out that instead of using a list here, we can use another feature of this library as follows. Instead of using a writer, there's something called a dictionary writer or dict writer that takes the same argument as input, the file that's opened. But now the one difference here is that you need to tell this dictionary writer that your field names are name and number. And let me close the CSV here. Name and number are the names of the fields, the columns in this CSV file. And when it comes time to write a new row, the syntax here is going to be a little uglier, but it's just a dictionary. The name I want to write to the dictionary is going to be whatever name the human typed in. The number that I want to write to the CSV file is going to be whatever the number the human typed in. But what's different now about this code is by simply using a dictionary writer here instead of the generic writer, now the columns can be in this order or any order. And the dictionary writer is going to figure out, based on the first line of text in that CSV, where to put name, where to put number. So if you flip them, no big deal. It's going to notice, oh, wait, the columns changed, and it's going to insert the columns correctly. So just, again, another more powerful feature that lets you focus on real work as opposed to actually getting tied up in the weeds of writing code like this otherwise. Questions on this one as well? But what we will do now is come full circle to some of the more sophisticated examples with which we began. And I'm going to go back over to my own Mac laptop here, where I've got my own terminal window up and running. And I was just going to introduce a couple of final libraries that really speak to just how powerful Python can be and how quickly you can get up and running. To be fair, can't necessarily do all of these things in the cloud, like in code spaces, because you need access to your own speakers or microphone or the like. So that's why I'm doing it on my own Mac here. But let me go ahead and open up a program called speech.py. And I'm not using VS Code here. I'm using a program called VI that's entirely terminal window based. But it's going to allow me, for instance, to import the Python text-to-speech version 3 library. I'm going to give myself a variable called engine that's going to be set equal to the Python text-to-speech 3 libraries init method, which is just going to initialize this library that relates to text to speech. I'm going to then use the engine's say function to say something like, how about hello, comma, world? And then as my last line, I'm going to say engine.run and wait, capitalized as such, to tell my program now to run that speech and wait until it's done. All right, I'm going to save this file. I'm going to run Python of speech.py, and I'm going to cross my fingers, as always, and
hello, world.
All right, so now I have a program that's actually synthesizing speech using a library like this. How can I now modify this to be a little more interesting? Well, how about this? Let me go ahead and prompt the user for their name, like we've done several times here using Python's built-in name function. And now let me go ahead and use a format string in conjunction with this library, interpolating the value of name there. And at least if my name is somewhat phonetically pronounceable, let's go ahead and run python of speech.py, type in my name, and
Hello, David.
OK, it's a sort of weird choice of inflection, but we're starting to synthesize voice, not unlike Siri or Google Assistant or Alexa or the like. Now we can maybe do something a little more advanced too. In addition to synthesizing speech in this way, we could synthesize, for instance, an actual graphic. Let me go ahead now and do something like this. Let me create a program called qr.py. I'm going to go ahead and import a library called OS, which gives you access to operating system related functionality in Python. I'm going to import a library I've pre-installed called QR code, which is a two-dimensional barcode that you might have seen in the real world. I'm going to go ahead and create an image variable using this QR code library's make function, which per its documentation takes a URL like one of CS50's own videos. So we'll do this with YouTube /xvfzo5pgg0. So hopefully that's the right lecture. And now we've got image.save, which is going to allow me to create a file called qr.ping. Think back now on problem set 4 and how painful it was to save files. We'll just use the save function now in Python and save this as a ping file, portable network graphic. And then lastly, let's just go ahead and open with the command open qr.ping on my Mac so that hopefully this just automatically opens. All right, I'm going to go ahead and just double check my syntax here so that I haven't made any mistakes. I'm going to go ahead and run python of qr.py, enter. That opens up this. Let me go ahead and zoom in. If you've got a phone handy and you'd like to scan this code here, whether in person or online, I apologize. You won't appreciate it. Amazing. OK. And lastly, let me go back into our speech example here, create a final ending here in our final moments. And how about we just say something like this was CS50, like this. Let's go ahead here, fix my capitalization just for tidiness, get rid of the name. And now with our final flourish and your introduction to Python equipped, here we go.
This was CS50.
All right, we'll see you next time.